So when we're talking about quantum mechanics, usually we're talking about the Schrodinger equation, right? So h of psi equals I h bar equals the derivative by the time derivative times psi. So this is your basic Schrodinger equation, right? Now we could get into Dirac and why, you need a relativistic version of the equation, or which is, that will lead into the Willett-Wood equation, which I just had written up here. Well, essentially all this is saying is that you have your Hamiltonian operator and your wave function is equal to the energy of your wave function. And this is kind of all we need to know for the time being. So what does this mean? This is Greek to us, right? So we'll get rid of it, and we'll just go through a basic overview of textbook quantum mechanics. I'm not going to go too super in depth with it. So we're going to say we have we'll draw a quantum harmonic oscillator over here, and we're going to have our states A plus B and A and B. So you have your wave that is evolving according to the Schrodinger equation with time, or with respect to time. So down here in psi of 0, we're going to start and say that our psi of 0 for this state is going to be wrong. This is technically a wrong notation. PhDs, we can get into it in the questions afterwards on why I'm choosing to do this. This is a qualitative talk that's kind of, again, meant to bridge the gap between the PhDs and the layman. Try to make these ideas accessible to everyone. So PhDs know this is a Straussian communication, that there are some things that I know are wrong, but you can probably you'll see. You should be able to see what I mean. Now, for the people who aren't PhDs in the audience that don't quite know where this is still pretty much gibberish to you, just keep following along. This is as in depth as you're going to need to get into. So we're going to have this down here. So this is our first entangled state. We're just going to say that it is A plus B. Okay, and so then as we evolve it to psi 1, psi 1, so technically we would want to, we're squaring our wave here to get a probability instead of a wave. So then this would become squared. And so then over here, our new entangled state is going to be 1 divided by the square root of 2a plus 1 divided by the square root of 2b plus. And so this is how our state evolves. We then flip a coin. So we have a 50-50 state here. We're going to say that tails is B, heads is A, and the coin is tails, so we know that our state evolved into B. So we can now erase this and erase this, because we know that the wave function collapsed onto the state that we had associated with B. Now there's not getting too deep into why this is inherently wrong. General relativity doesn't work with this renormalization process. What general relativity does work with is a wave function evolving according to an appropriate version of the Schrodinger equation with no collapse. So it's not that GR and quantum mechanics are incompatible. It is that GR and the collapse postulate of certain interpretations is what doesn't work with quantum mechanics. So we can say that we can find our reality as a vector in Hilbert space, right? Because in Copenhagen, the textbook version of quantum mechanics, we just get rid of the other state, it goes away. We renormalize the process. That's what we do with the energy. When it's just some wishy-washy process, and almost everybody admits that it is incomplete. Taking the Everettian point of view, or the many worlds point of view, as I said, that reality is a vector in Hilbert space, right? So how can we think of this? Well, we can think of a blow sphere, right? So we have our qubit over here. We're going to have some point over here at some elevation angle theta, and it has a meaningful angle phi. This is going to be r, so we have a coordinate of r, theta, phi. Now, how does this relate to this? Well, any point of r can be associated with one of our states. So in this two-system state, just if the coordinate's up here, we can say it's A, and if the coordinate's down here, we can say it's B. So A and B, and this is starting to get into, what spinors are. We don't really need to worry about spinors today for this talk. Okay. So we have this picture. What's a different way we can look at this? So let's look at a cubic state here. So there's always going to be some area here associated with this sphere. So you're going to have the area of your sphere, and there's going to be some entropy associated with this quantum system. And so what is so the dimensionality? So your DIMH, your Hilbert space, the order of E to the S. Well, what is S? S is our entropy, and we're going to say that here today that we can define entropy as our IR unit divided by our U V. Now, technically, we could count infinitely many, infinitely large wavelengths and infinitely small wavelengths in our quantum system, right? But what's a reason that we might not want to do that? Well, if we count more than a certain amount of, if we count down on the smaller wavelengths, down below a certain amount for any given area, or for any given system, that's what the IR is, the large parts of the longest, like the longest wavelength that you could fit in your system versus the smallest. Getting slightly ahead of myself here. If you count more than a certain amount of these per this, the system is going to collapse to a black hole. And we know from Bekenstein and Hawking that black holes have a finite entropy, right? So we can say again, the entropy here is our area divided by our Planck area. So area divided by Planck area. So we just count the area of our system here in Planck areas, and that is its entropy. And so then that entropy number becomes the exponent for here. Now, why is that? Remember, we have to think of this Bloch sphere as a shell. So if we scraped off one radius coordinate with a freedom on the outside, that's going to change your entropy. It's going to change your area of the system, which then changes the entropy. And so you get this this system, where one is dependent on the other. So you have, so we can write now that A is proportional to S, where the area is proportional to entropy. Okay. So where is this going to start coming in handy for where we find general relativity? Okay, well, where this is good, we'll erase this 2 now for the time being. This here is proportional to S. So we know that area is a measure of geometry. It tells you something about the geometry of your system. So we can relate our area to some type of spatial curve, some spatial curvature. Through spatial curvature, we can relate it to the G00 aspect of the Einstein tensor. Einstein tensor, spatial. And then on the other side here, so we have our entropy, our modular Hamiltonian, through the entanglement first law. And our modular Hamiltonian can be associated with T00, or the energy density of the system. And when you have T00 is proportional to G00 through Lorentz invariance, we end up with G mu nu being proportional to T mu nu, which is just general relativity. That's Einstein. So this is entropic gravity in a nutshell, and why general relativity does work with Everettian quantum mechanics, the many worlds interpretation. but it does not work with other interpretations, which is why people try to sell the quantization of gravity as something that we need to do. But that's only, we don't need to quantize gravity when we have entropic gravity, and that's what this is. So, what is a way that we can draw this out to more represent, get back to our quantum state here? Well, we can do it with a hyperbolic tessellation, right? So we'll just the red one first. And this will only take a second. So we have this hyperbolic tessellation. On this side, counting all of these nodes in here, it's going to be our entropy. So there's always going to be a certain amount of entropy that fits within any given area. And so we could do this for the whole system, or we could count off any one of these smaller little nodes and make that our system of focus, and this area entropy law will still hold. So therefore, general relativity will also still hold. And just to try to help bring the visualization back to our quantum system, we'll redraw our quantum oscillator, where deeper in the well, it's going to be where your current position in time here, which is going to be more near the center of this. And then this becomes our area, and then these become your entropy. So this is kind of a map of one of these levers. So, we can map one to another here. So this starts to bring up the question, how does one go about traversing this this object, this multiversal landscape that quantum mechanics seems to provide for us? How do we escape from one of these? Well, let's turn to Penrose for a bit. So Penrose had some good ideas with this, with his orchestrated reduction. So what is his OR? So it's going to be the order of sign instead of equals, because it makes me more comfortable. H bar divided by G, gravitational self-energy of the system. So this should look a lot like the H bar divided by E equals T of the Heisenberg relations. Okay, well, what does this mean? So A plus B and AB, as it progresses through time, so there's going to be some gravitational, I'll go to green now, so there's going to be some energy, the gravitational energy of the system, and this state will be different from this state. And so what this tells us is that the time, T, the time, so that this decoherence happens, is going to be based on this H bar divided by E, the system. So the more energetic the system is, the faster it is going to happen. Now another way that we can write this is that when this separation becomes bigger than H bar is when we say decoherence happens. So that is when the splitting happens. Now, take this, we can rewrite it. Why? Because C equals 1 equals H bar. H bar equals E times T. So, because C equals 1, we can replace this with C, replace these with C, and what happens with is these branches, as the weight gets larger than H bar, they start decohering faster than the speed of light, which is why we don't normally interact with these systems. You need to be able to go faster than light to traverse between these. Now, that being said, do we know of anything within the framework of quantum mechanics or general relativity that can be used for potential faster than light phenomena? Well, stuff like wormholes and warp drives in the context of general relativity. This is backed up in a 2021 paper by Dr. Yuri Eroshenko, called Escape from a Black Hole with a Spherical Warp Drive. He proposes the WD equals EPR paradox to go complementary with the ER equals EPR, not paradox, conjecture, excuse me. So essentially that warp drives and wormholes can be used to escape from the event horizon of a black hole, or to jump between one of these eigenstates here. And that they really, because again we have found that general relativity is a semi-classical approximation of the entropy of or the entanglement entropy of our quantum system here. So anything that we can write in GR is really just a semi-classical approximation of some entanglement. And so that gets, when we start to view a warp drive in that lens, really what we see is it's an entanglement machine that can jump between these eigenstates because it can go faster than light. So, yes, in order to understand a little bit more about warp drives, we are going to need to now take a break from the quantum mechanics and jump into general relativity, what a warp drive means within that context. And there's some of the things that we can probably start to do with this. We'll keep some of the pictures that we had here in the back of our mind. We'll come back to them later. So, if we're talking about general relativity, it's going to be that G mu nu equals 8 pi G divided by C to the fourth T mu nu. So, what does this mean? This is literally Greek to me, right? We use that euphemism here a lot. So, it's that space-time curvature tells matter and energy how to move, and the matter and energy distributions tell space-time how to curve. So, energy affects geometry, and geometry affects energy. You know, the same relation as our area proportional to entropy. We have geometry proportional to energy. So, what do we start to mean when we say this? Let's do the visual representation first. So, we're going to have these map of space-time, G mu nu, and then inside of it, T mu nu. So, energy tells space-time how to curve, space-time tells energy how to move. So if we're going to flatten this back out, you know, you keep this picture in your head. I'm sure you've seen something, you know, some stuff similar to it. Let's just flatten this out to focus on only one of those geodesic lines. So we're going to have our G mu nu, our space-time well. This is what the people mean by your gravity well. And it is going to be your T mu nu, G mu nu. So this is a way that we could flatten out, you know, a 2D map down to a 1D one, just so you can see what's going on here. Now, if you want to complexify this a little bit more, just to kind of give you guys an idea of what's going on with this, we're going to write out the actual tensors. So we're going to say that our G mu nu equal to, and on this side we have the T mu nu. So on your T mu nu over here, you have your T0, 0 is your energy density, like we talked about earlier. Your 1, 1, 2, 2, and 3, 3 are going to be your pressure. These blue ones here are your momentum flux. The ones here are your shear stress. Over here you have your energy flux, and here you have your momentum density. We're not going to worry too much about this today. We're going to worry more about G mu nu, the Einstein tensor. So, I'll go back to my blue here for a second. So if we have our space-time axes here, essentially we're making a space-time globe. So we're transferring a map, a globe of like a 3D sphere, and we're projecting it onto a 2D surface and making a map for it. So your TT will be for your time axes. So I'm not going to draw the time axes here. Might get a little too confusing. So your XX, your YY, and your ZZ. So say if this is like our X and Y axes, this tells us the relative lengths of each one of these squares and what these should be. The reason they go down here is the TT, XX, YY, ZZ. Clock is your T, your T coordinates, your rulers are your X, Y, Z, and then the protractors between the rulers are these adjacent ones up here. So you have your 4 Cartesian coordinates and your 6 protractors. So 1 clock, 3 rulers, 6 protractors for your 10 PDEs that you have to make. So reeling this back into warp drive, well, in 1994, Dr. Miguel Alcubierre, he, inspired both by Star Trek as well as the expansion of the universe, for coming up with a G-mu that was capable of superluminal velocities. Because remember, nothing with mass, according to relativity, can go faster than the speed of light, but space-time itself can. So that's a very good loophole for us to exploit here. So, keeping this in mind, just remembering whatever goes in over here will affect the energy requirements over here. So this is what Alcubierre did, is he started with a shape and he found out how much energy is that shape going to require. And we will get rid of this for right now. So, if we're going to talk about warp drives, we need to bring this down now. So G-mu. We can write this in something called a line element, okay? So we're taking our X, or our TT, XX, YY, and ZZ here. So because there's 2 of each, so making our DS squared, our space-time geodesic, with the shape of that. So you have point A, point B over here. You're basically doing Pythagoras' theorem. So this is going to be your dx, dy, and then it's a squared plus b squared equals c squared, but this is for curved space-time, so this is going to have some curve to it. We're finding the length of this curve, so this is going to be our ds squared. ds squared. So now that you know what this kind of is supposed to mean, at least enough for this talk. So it's going to be. So we have to specify a metric. I'm going to be using the plus minus 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 metric for this talk. We could use the minus plus 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 metric. You just have to establish which one. I digress. So dt square minus dx minus dy minus dz squared. Okay, so trying to reel this back into warp drive, we're getting some shape that will be represented by this by a version of this equation here. So what is that shape? What we found out is that ds squared equals dt squared minus bracket dx minus v f r dt squared minus dx minus dz dy minus dz squared. So what does this mean here? Well, this is for a warp bubble moving with a geodesic in the x-axis with time, okay? So moving with some velocity, v, on the x-axis through time, divided by some shaping function. Now Alcubierre, has r be a shaping function to denote pretty much a spherical warp bubble. And so if we're going to go back to our 1D map of the G-mu and the T-mu, what might this look like? So we're going to have our space-time geodesic, positive well, flat space-time, negative well, positive, negative. Yeah, inside of it is our T. And this is your warp drive in a nutshell. You can see that there's your to draw some line of energy gradient. This makes a hill right here. The ball rolls down the hill would be a kind of a bad analogy to use, and what gives you your velocity. So this is our warp drive, which, remembering from earlier, is actually a semi-classical approximation of some entanglement structure, right? There are some problems with this, though. One of which being it violates the positivity conditions, which may or not be an arbitrary constraint put on by Hermann Bondi in 1957. That's a different talk. But also it needs like 10 times the amount of observable mass in the universe, or mass in the observable universe, which is problematic to say the least. Now, there are, like this came out in 1994, we're in 2024, there's been 30 years of, various academics and PhDs have been working on this to really drive these energy requirements down. So, I guess we could either look at what some things are that people have done to lower these energy requirements. Actually, let's do that first. We'll get rid of this because we don't need it anymore, but we do maybe need this. So, well, one of the first things that people have done. So, Dr. Harold Sonny White of NASA Legal Works Laboratory, he played with the equations a lot, and he figured out you do two things. One, you make the bubble thicker. So I'll redraw this to be a little bit more accurate to Alcubierre's representation, so we can see a little bit better on how some of these people have said to improve this. This would probably be a better representation of Alcubierre's bubble. So, what Harold White did, he did two main things. First thing is, this is too thin. We're approaching 100 times the magnitude of the Planck length, which is really thin. And then if you know that you're going to have energies commensurate to fill that. We're not going to get too. I'm digressing. So, just going off this, first thing that he does is he makes the bubble wider instead of thinner. So the distribution of the energy in the bubble isn't as concentrated, and actually this helps to lower the energy requirements. The second thing that he did is he pulses the bubble. Actually vibrates it, and apparently this softens the stiffness of space-time and makes it easier to engineer. According to him and his work, I can link his papers in the description for you guys. So it's already two things that he did to get the energy. Just doing that, he got the energy requirements down from 10 times the amount of observable mass in the universe. Natario got it down to solar and planetary size masses. He gets it down to about 700 kilograms worth of mass energy by this method. Now, this isn't the only method. So we're changing the shaping function. We're making it more complex. We're vibrating it through time. We're changing the shape of it a little bit. We'll keep going with this intuition to alter the shaping function. So Charles Barcelo, he came along and he made another observation. He's basically said, well, the choice for a spherical bubble is really just it's an arbitrary choice. There's no reason to choose one or not to choose one. It's just again arbitrary. The decision to use a spherical bubble it makes the equations a little bit more handy to work with. It's like the old jokes. Assume a spherical cow. But so what does Barcelo does? So we're gonna rewrite our warp drive metrics of ds squared equals dt squared minus dx minus vf or vf, our shaping function. But instead of r for a radius, it makes it an x, y, z. technically it was XYZKT the whole time. Each Alcubierre here chooses to make it a spherical bubble. K being the scalar constant up here, by the way. dt square minus dy square minus dz square. So what does Bresella finds out? Well, he finds out that if you just change the shape of the bubble now, not only does the energy requirements go down a lot, so does the need for negative energy starts to go down a lot too. Now there are other people like Chance Glenn, Eric Lenz, Lavinia Eisenberg. I could name quite a few that have gone and shown that you can actually have positive energy only energy requirements. But so what Bresella does is he goes with a tic tac or elliptical shaped warp bubble. Actually, I'll make it red to keep it consistent with our theme here. So instead of a sphere, he makes it as elliptical. That again lowers the energy requirements even more. Lower the energy requirements from Alcubierre as Notario's. He didn't plug this into whites, though I do believe Fernando Loop has, and that did work, as well as Preciano's. So there's actually quite a few ways that we can get this down. So yeah, so if you start to combine all of these, some of these different various methods, you change the shape of the bubble, you change the thickness, you pulse it, all that's already doing a lot to really lower our energy requirements into something that's probably a lot more attainable. So Preciano introduces another term in here, a x, y, z, k. Adding this in again to make the bubble more dynamic. Again, he claims that you can get it down to arbitrary levels, and I think if you're combining all of the above, you probably can get it down to really a lot lower energy levels than is thought of in the mainstream. Now, on top of this, we can also look at Sarfati's model. Now, what does Sarfati say in essence for what to do with this? Actually, before we go into Sarfati, I will change this to a positive. Well, because we can now. Because we said we can. So energy requirements are already a lot better just off of playing with the shaping function. Now, if you look at Sarfati's work, if we're turning into here, well, what is the speed of light? C, electromagnetism, is 1 divided by the square root of epsilon and mu naught. Or you can say is epsilon, it's E not an epsilon, mu naught squared. So, if we're doing this, we can plug this back in and reformulate Einstein's equation. And I can do that right now. So G mu nu equals 8 pi G, and then because how we're reformulating this, it's no longer divided by C to the 4th. It's times epsilon, or it's E not an epsilon. Epsilon naught mu naught for the permeativity of the permeability of the vacuum. And normally you would just square this here, pop this off here, and put the T mu nu back in. But he's taking it even a step farther and is saying, what about general relativity in matter itself? Especially things that might have a tunable refractive indices, like certain metamaterials, which metamaterials is his whole thing. But there's might be. I'm digressing. We'll just stick with this. So. This here, and then we'll put another bracket in because we need to. He talks about from warp drives. You want to do the near fields of those. So he writes. So we put another 1 plus near field of epsilon, and 1 plus mu. So this is what Einstein's equation then becomes. So the K here is this scalar constant term. So when we plug this into here, and I could rewrite out the whole. Actually, you know what? I will rewrite it because I have the power of editing. So our equation starts to become something more like this. And again, this is going to start to drastically alter the energy requirements for on the T mu side of our equation over here to get the warping of T mu. So when we start to combine all of these various improvements, Sarfatti, Barcelo, White, we can't just look at one modification of Alcubierre. We need to look at all of them and start to combine the best ones that are compatible. When we do that, we start to view that Sarfatti might be actually very correct in the sense that we could probably do this with pretty low energies if we have the right material. Now, if we don't have the right material, we can still do this. We just need a shitload more energy. Excuse my French, it's just the reality of the situation. But not impossible if we get something like fusion or 0 point, if 0 point is even a thing. There's the caveat on that. But let's just say we get fusion unlocked right now. You can do this with fusion. If you had fusion and superconductors, you could do this. But then we could use the profits from that to start getting better and better optical properties of metamaterials, so we can start to do the thing, right? So we've gone over the multiverse, the quantum multiverse and warp drives, right? Because we need again. So where does the warp drive? Where does this become back into our quantum mechanical multiversal picture? It's because that for traveling, this is the mechanism that we need to travel faster than light, and faster than light travel is the mechanism that we need to jump between the eigenstates, or between the various branches of the quantum multiverse here. So what might that look like? So let's erase this here. So I guess we'll draw back out our quantum wall over here. We got our energy, our different energy states. We're farther in time here is closer to the center of our visualization over here, and each one of these nodes, the entropy of what these different systems are. Well, let's repaint this picture. It's sort of something a little bit closer to like a space-time diagram. So we are looking at something like a block universe now. So this is going to be our. We'll come over here first, and we'll do some more caveats. And I know there's people are going to say that this is wrong because you just shut up and bear with me for a second. We need like our Minkowski diagram, which people are going to say is wrong for this type of thing, but just bear with me. You guys will know what I'm trying to represent, and we'll get the nitty-gritty of my visualization later. And often, and the Yuri Oroshenko paper that I mentioned earlier does use this graphic. So faster than light travel, point A, point B is going to be outside of your light cone, and you're going like that, right? Now, I know there's going to be people screaming at me in the comments already, no, that's wrong. There's going to be two different answers to this. There's going to be some people that are going to say that our null geodesics are actually skewing, like scissors as our velocity becomes relativistic. And then there's going to be other people that say that that you're actually rotating your light cones to get them to overlap. I'm aware of these caveats. This is just makes for easy visualization. So for those people that are more comfortable with those graphs, just know that when I'm drawing something like this, we are using it to represent that. Okay, so now that caveat's out of the way, really, a straight line would be for a constant velocity, right? Well, we know that it's not going to be constant velocity because you're starting you're resting in your local frame. So you need to accelerate away from wherever you are, slower than light, and then eventually you cross some transition to the superluminal regime. So again, these are our null geodesics, so light always goes on these 45s. And coming here, and then eventually we transition. And we go into this tachyon regime. And we start going faster and faster than light, until we want to slow back down again to our wherever our target location is. And you will see that this made something sort of like reminiscent of a wave. Keep this in mind. We're going to transfer this over to this, because remember, this was just for one space-time coordinate we're trying to travel between the coordinates in the multiverse because we're taking serious the notion that we can travel outside of our light cone. And when we say traveling outside of our light cone, we mean getting our light cone to overlap with another adjacent light cone. So, say that we are in this branch over here. We want to go to this one. So we're going to say we're going to start here, and we're going to go slower than light until we hit our point where we go back. Then we start intersecting through some of these ones, and then we come and slow down over here. Now, how do we get back? We need to make a 2 jump movements. We need to do 2 different warp events if we want to get back to the same point that we started, or potentially earlier in the same timeline, and we can potentially explore arbitrarily any of the coordinates in this system. Now, we could also probably say that time is closed. If this was a closed universe, you could probably, much like you go the same way in a globe, you could wrap around the circle. You could probably do something similar where you go all the way, extrapolating out through here. Or you could come back and travel that way too. You could probably do either. I don't know I'm sure fuel would dictate, what your what geodesic you decide you want to travel. So that's probably a good segue. So really, if we're going to expand this here, we can start to think of. So let's erase this. We're going to transfer over. If we apply this concept to our blow sphere here, really, what each one of these becomes is an S2 sphere, a 2 sphere embedded in the 3 sphere connection. And again, this is where the picture starts to get interesting. Remember, we can apply this spherical coordinate into this system. All right, so if we put some line in here to go off as our baseline, any one of these points on here, at least in this 2D circle, can be represented by an r theta angle, because it's becomes like a phase space almost. Well, this becomes our time fiber, and really soon, so time becomes a U1 or an S1 fiber. So you'll have this. So R becomes T. So our R over here becomes our time parameter. So theta angle. And again, so this extrapolate this out to a sphere also. This is a S3 hypersphere. So spheres embedded in a hypersphere via the one sphere. Because remember, we said this is a lot like a spinner, where once you get out here, you kind of teleport, even though it's not actually a teleport. It's a topology trick. I'm sure that the PhDs in the audience are probably going to know what I'm talking about. The people who don't, just look up spinners in the Dirac equation and mass shells, and you'll see what I'm getting at here. So this becomes our S1. So when you have your your S2 spheres being connected via S1, so your S2 spheres being embedded within your hypersphere, with your S1 fiber being the connection, being the connection that makes up the phase. We see that the phase space of the multiverse is as in essence like the Hopf vibration. So each timeline can be considered one of the S1 fibers in the larger fiber bundle. So as we're looking at time now as our R parameter on our block sphere, as well as being a U1 fiber or an S1 fiber, we can rewrite again Einstein's equation a little. We're going to add a term to it now. So we're going to look at specifically we're going to look back at the line element. So our ds squared equals dt, and because t is now the r coordinate in our spherical coordinates for our block sphere, we're going to add a theta phi parameter to our line element. So that the t parameter, being our r, will tell us, which layer of the onion we are in, and then the theta and the phi parameter will tell us which sphere in the hypersphere, so which part of the onion we're in. So we get the layer and the part of the sphere, and then within the two spheres, when our regular x, y, z Cartesian coordinate parameters are going to come back into play. So this starts to give us a very basic framework in how we can traverse our multiverse here. Because if we're going to go back to this diagram that we made right here, well, if we put an arbitrary line here, there's going to be an extra distance that's put in because these will have the same t coordinate at this level, but in this case the theta angle would be different. So we have to add this into our geodesic to help give us the distance, and then that'll help give us the energy requirements for what the warp drive is going to need for that particular warp event. And what we would normally consider as a travel between different branches, well, we need to consider a Lorentz transformation now for the system. What might a Lorentz transformation for the system look like? It will look about like this. So you'll see the hyperbolic tessellation here with being represented in the VR, and as you walk through it, you'll notice that the shell wraps around you and the observer always stays in the center of the system. This is very reminiscent of Einstein's equivalence principle, where whether or not you're moving the universe through you or pulling the universe around you, it's the same amount of energy. There's no difference. So, really, when you're running a warp drive, you're to travel between these different eigenstates, these different branches of the multiverse. You're performing a Lorentz transformation, sort of like that visual that I just put in here. So where are we going to go with that? So we covered the essence of multiversal travel, the basics of quantum mechanics, how you can find general relativity in quantum mechanics, and then how you're going to use a warp drive to travel between these branches, what a Lorentz transformation might look like, and a plethora of different ways to lower the energy requirements for a warp drive. It explains a lot about like the UAPs and the recent science around them. Some of the quotes, like Burleson saying that they were told in this gift that they phase into our reality. Well, this is the phase space of the multiverse, so that makes sense. Yeah, no, time travel is multiversal travel, and you need a warp drive to do it, and it's all semi-classical approximation of some larger quantum entanglement. I guess we'll cut that there.